Okay, so good morning. I thank Suman for introducing some of the things I'll need, which I'll gloss over quickly. So what I'm going to talk about today is motivated by our interest in the same problem that Suman talked about, which is understanding yielding in amorphous solids. But we have been looking at this problem through cyclic deformation of amorphous solids. But what I want to tell you today about is sort of a sidetrack that, that has arisen in this study, which has motivated us to look at ways of generating well-annealed glasses. And this is sort of a broad generic problem. How do you find deep minima in a rugged energy landscape? So we have some interesting ideas on that which I want to share. Very briefly, I will say a little bit about amorphous solids and yielding and cyclic shear deformation of glasses and liquids. And mostly I'll focus on this point, whether this procedure, which is an experimentally well-used procedure for looking at mechanical behavior of all kinds of solids, also helps us generate on the computer well-annealed glasses. Okay, and at the very end, I'll come back to the yielding problem for two slides to tell you what interesting new physics arises when you do look at well-annealed glasses. Okay, so this is work done by the people mentioned here. Himanshu Bhaumik has a poster which you may want to look at for more details on this last point. Okay, so this is just a poster slide just to say that yielding and mechanical failure is interesting in a broad variety of problems and situations. And as compared to crystalline solids, when you look at this problem for amorphous solids, a key difference is that the glass or the amorphous solid that you study is not unique. It depends on the preparation history, and in turn, the properties and the yielding behavior, as again mentioned in the previous talk, depends on this preparation history. Okay, so this is sort of a quick movie of what we do. We take an amorphous solid, which in this case is a local energy minimum structure. We study this in the initial part in the zero temperature limit. It's called athermal quasi-static shearing. And we basically shear these solids back and forth, and we look at what happens. And the model system that we study is mentioned here. It's not very important for the main points I want to make. And so in our initial study of yielding through this procedure of cyclic shear deformation, we found something that was interesting, which is if you look at what happens to the energy of the glasses as a function of increasing numbers of cyclic deformation, you observe that the energies sort of change and go to some steady states. And if you look at this asymptotic energy values, I mean, here actually they don't quite go to the steady states very convincingly, but this is just to illustrate that it changes with cycles. And if you look at the asymptotic energies as a function of the amplitude of shear deformation, which is the only parameter when we're looking in the athermal limit, you find that this asymptotic energy both depends on the initial glass that you started with and appears to have a minimum very close to what we identify to be the yielding transition. Okay, I won't go into that part of the story now, but this suggested to us that if you were to shear a glass close to the yielding point but below, this might be a good way of generating well-annealed samples. Okay, and that idea we take forward, and instead of doing the athermal quasi-static procedure that I just mentioned, and the data in the previous slide was for that limit, we now sort of adopt a finite temperature, finite shear rate simulation procedure. One way of thinking about it is that this somehow will expand the various mechanisms by which your glass may relax. So actually, when we do the finite temperature, finite shear, we're actually simulating liquids rather than glasses. But in order to monitor how well a glass may be annealed, we look at local energy minima and the corresponding energies, okay? And the idea is that maybe a suitable combination of these parameters, temperature, shear rate, shear amplitude, will give us an approach to generating well-annealed glasses. Okay, so very quickly, what we do is something called slot dynamics, where you impose shear at a given shear rate. In our case, the shear strain is a cyclic oscillatory function of time, and okay, one can write the equations of motion in this general form, where depending on which thermostat you use and whether you're using a stochastic one or not, you have a random force term and a friction term, and I won't go into further details of that. Okay, so what do we find? So here is one particular study where we look at a fixed temperature which is kept very low, and I won't dwell on reasons, but basically it corresponds to the best temperature range in which to work to get maximum annealing, and a fixed shear rate. And I'm showing data by varying the amplitude of shear, okay? And what you find is two things. One is, if the amplitude of shear is too high, you don't actually get much annealing. But in all other cases, with the number of cycles, you keep going to lower and lower energy states. And the behavior, and this is also interesting, but a sidetrack I won't go into, is logarithmic, okay? And logarithmic relaxation normally is very slow, but then it's faster than super Arrhenius relaxation, okay? Anyway, based on data like this, we can identify what is a good temperature range and shear rate to work with, and you get, if you fix the temperature and the amplitude of shear, as I've indicated here, one can vary the shear rate and look at what happens. And basically what we find is that we can go down to very low energies, and the gain in time compared to normal molecular dynamics is about 3 orders of magnitude, which is encouraging, but not a record in glassy simulations of late. But there are reasons why this may be an interesting approach to follow. And here I compare the lowest energies that are obtained by normal simulations using normal amounts of effort, and we managed to go down to much lower energies, okay? Okay, and so one can ask, okay, so you're doing something which is driving the system. How is this going to compare with equilibrium, so are you generating an ensemble that has anything to do with the equilibrium ensemble at the temperature you may be trying to simulate? And the empirical evidence is that, in fact, even though we can't guarantee it, under suitable conditions, we do get equilibrium properties of the glasses that we generate. But since there is no guarantee, you can ask, and one of our referees did, how can you do this as a well-defined equilibrium sampling method? And the answer turns out to be yes. And the basic idea is you adopt a philosophy that's been employed in hybrid Monte Carlo, where you use molecular dynamics to generate a trial configuration, and then you do normal metropolis sampling, okay? I'm looking at the clock, I don't have too much time, but this works with the normal energy difference going into the metropolis acceptance if your system is not thermostated. But if your system is thermostated, then that's no longer the correct acceptance criterion. Instead, one has to look at how the phase space volume, which needs to be preserved in order for normal hybrid Monte Carlo to work, you have to look at how the phase space volume fails to be conserved and correct for it. And basically, you have to look at phase space volume contraction, and this is given by heat dissipation. So you can add an extra term in your acceptance rule that takes account of the heat dissipation. And so the upshot is, instead of using the change in energy of the system, you have to look at the work done. The same can be also obtained by employing Crookes' theorem. So we have an equilibrium sampling scheme, but does it work? So the quick answer is, when we tried this out for small systems, it worked okay, because when we look at the work done, this is a histogram. For small systems, it's both positive and negative as I look at different cycles. But when you go to larger systems, this seems to fail, okay? Because on average, the work done is positive. And so does that mean this doesn't work anymore? And the answer is no. You have to be a little bit more clever and patient. Basically, the one trick that I've figured out which works is to not shear the entire volume, but to pick a random subset, a subvolume like indicated here, and then the work done does fluctuate around 0, and you can have reasonable acceptance ratios. And now, so this is sort of a very quick picture of some of the recent results. This is ongoing work. Basically, you know, I'm showing data for the equilibrium sampling through just a normal MD at a temperature where I can do it. And then sheared simulation where I don't do any correction. I don't do a Monte Carlo. And then this is a bad case where I choose my amplitude to be too high, and then the energies that I get are not the equilibrium energy distribution, but with the metropolis acceptance step, I do get basically the equilibrium distribution in energies. And then two other quick points is, it turns out that the thermostat details do matter a lot. You get better annealing with underdamped simulations, which is an interesting thing to use. And the subsystem shearing that I mentioned also gives you annealing, though the efficiency is a little bit lower. Okay, so I don't have time for this, but so this is how you generate well-annealed glasses through cyclic shear. Is it going to tell us anything new about the physics of yielding and glasses? And the answer is a rather pleasing yes. Here is the energy versus strain amplitude results. Now I'm going back to athermal shear, and what one finds is that as a function of the annealing of the glasses, there's a dramatic change in behavior from ductile to brittle behavior, and more interestingly, that the transition seems to happen at an energy that's associated with the mode coupling crossover in the system. More details in the poster of Himanshu, and I stop.